we already did this before. So charge moving at rest, or charge at rest, you can see the charged particle doesn't move at all. So it experiences no force from the magnetic field. Now, if we were to double the speed, or if we actually have it moving parallel to the field, we also know that there is no deviation in motion, hence, again, no force is being experienced. Now, if we're perpendicular to the field, we can see that we get a circular motion, okay? So there's that. We have positive charge, negative charge, and then our zero charge. Now, what if we change the speed of the particles? So we have v1, 2v, and v3. You can see that, relatively speaking, you need a bigger force to maintain this charge to come back in this circular motion. All right, so following from our depiction of how charged particles will only experience a force, or it will experience the maximum force if it's moving perpendicular to the magnetic field, and if it's parallel. So let's say if our charged particle was moving parallel to the magnetic field, we experience zero magnetic force. If the magnetic field is moving perpendicular to our moving charge, it will experience a maximum magnetic force. So that's what we talked about before in the previous lesson. But what we can actually see here is when it is perpendicular to the field, or regardless, so long as it's not parallel, the charged particle, the force it experiences causes it to undergo uniform circular motion. So you can see here, What that means is if it's undergoing uniform circular motion, we have a case where there is centripetal force acting on the charged particle. And given that it is undergoing uniform circular motion, there should be a radius value that we can calculate to work out, the radius of its circular motion. So let's get into deriving those formulas. Okay, so firstly, we know, given that it is undergoing uniform circular motion, it must be experiencing some form of acceleration. Now, if you recall, the formula for force is F equals to m times a. Okay, if we want to find the acceleration a charged particle experiences in a magnetic field, we know the force is given as 𝑞𝑣𝐵 equals to m times a. Okay, all we have to do is move m across here, and we work out what the acceleration the charged particle experiences as it goes through a magnetic field. Now, if the moving particle is not perpendicular, so charged particle is not perpendicular, if that's not perpendicular, then again, we could just rewrite this as sine theta over m. I should also state not perpendicular to the B field or the magnetic field. Okay, so we can rewrite the formula like this, and that would give us a formula to express for the acceleration a charged particle experiences in a magnetic field. So I'll clear that out, and I'll show you the formula. That's what we came up with. The other thing is we said that there is a circular motion component of this charged particle in this magnetic field. So we can equate the force from the magnetic field being equal to the force of the centripetal field. Okay. The reason being is the reason why our charged particle is going around in circular motion is because of that magnetic force. So we rewrite our equation like so. So this can actually help us work out the radius of the charge. So if I make R the subject, so it'd be mv, so the v's will cancel. So it's mv q b. Q can be divided over here, b can be divided over here, r can be shifted or timesed over here. And that's the formula for the radius of a charged particle that's going through a uniform magnetic field. Remember, this is for the scenario for a uniform magnetic field, meaning the magnetic field strength stays constant. And the last thing we can do is actually find out how long it takes for the charge to rotate around this magnetic field once. So from module 5, we know that the orbital velocity of a circular moving object is v equals 2 pi r over t. So it can be rearranged as r equals to m qb times 2 pi r over t. Okay, so that's what we have here. Now if I want to find the time, I can simply move t over here. So times t here to move it over. Okay, I can divide this r away. So it comes down here and it'll cancel out this r at the top. So the period for a charged particle to do one circular rotation or circular orbit is 2 pi m over q times b. And that gives us this formula here. Okay, so there might be questions where they might ask you how to do these derivations and then perform the calculations. Now take note, this formula for acceleration is not given to you on the data sheet. Nor is this formula, nor is this formula. So you'll need to be able to be confident enough to derive these equations by yourself, or at the very least, come up with the logic that we see here. Okay, so that's what we have. I'm going to go through some calculation questions in a separate video. So by all means, check that one out as well if you need help with doing these calculations. Anyhow, that concludes our lesson for today. So we've talked about the components that will increase the magnetic force on a charged particle. It needs to be perpendicular. The charged particle needs to be moving. For a stronger force, you need a higher charge quantity in coulombs and also a stronger external magnetic field. We also looked at what would happen if the charged particle is going through the field. It will perform a circular motion, and so we did all our derivations just then. If you found this video useful and the simulations helpful in understanding the concept, do give this video a like, subscribe if you haven't done so already, and I'll see you next time. Take care.